Linear Algebra Part 3. Okay, so in this section we're going to talk about determinants. Definition: a determinant is a scalar value associated with a square matrix that provides important information about the matrix, such as whether it is invertible or it has an inverse, the scaling factor of the transformation it represents, the orientation, preserving or reversing of the transformation, etc. Okay, so if A is a matrix with aij elements, okay, having a size n by n, meaning it's a square matrix, number of rows is equal to the number of columns, then its determinant is denoted by that of A, or A within an absolute value like pipelines. 2 by 2 matrix. A happens to be, so let's say A is equal to A, B, C, D. This is the matrix. That A, determinant of A, is equal to A, D minus B, C. Okay, so A, D minus B, C. Now, 3 by 3 matrix. This is called Sarus rule. Okay, so determinant of A becomes A11. So A11 multiplied by, okay, so let's see the intersection of A11 from a row and column perspective. Okay, so you have A11 here, and you multiply it by A22 times A33 minus, okay, minus A32 times A23. This is for the first element of this row. Okay, then you have always plus, minus, plus. Okay, just like in the cross product of a normal vector, you know, one-dimensional vector. So minus A12 times, okay, so let me clear the ink, then minus A12, which is this one here, and let's check where the row and the column intersect at A12. Okay, so minus A12 times what does not intersect, which is A21 times A33 minus A31 times A23. Okay, A21 times A33 minus A21 times A23, or A31 times A23. Okay, so plus, let's clear the ink, plus, so here again plus, minus, plus, plus A13 multiplied by, okay, let's check the intersections here between row and column, plus A13 multiplied by A21 times A32 minus A31 times A22. Okay, and this is how we get the determinant of A, which is a value. Okay, it's not a vector, it's a value. General definition for determinant, which is also called Laplace expansion. For any n by n matrix A, the determinant can be computed by expanding along any row or column. So determinant of A is equal to sigma, or sum from j equal 1 to n, of minus 1 to the power of I plus j. Okay, this is a generic formula, you don't need to bother with it. Okay, so minus 1 to the power of I plus j of aij times determinant of mij. Okay, mij is the minor of aij. So this is where, you know, you have, after intersecting the row and the column at aij, okay, which you will be multiplying by the minor matrix. The minor is, you know, these four numbers underneath it, this minimum matrix underneath it. So, okay, obtained by deleting the ith row and the j's column. Okay, we've seen it moments ago. So let's say you have aij within the matrix here. Okay, so you cross the row and the column where they intersect, you eliminate these elements here, and then you are left, let's say, with 3, 4, 2, 5. Okay, So it is aij multiplied by 3 times 5 minus 2 times 4. Okay, you get it? Now, if aij is an odd index, okay, it is situated at an odd index, okay, it will be plus. Then if it's at an even index, it will be minus, okay? So plus, minus, okay? Just as we've seen in the previous matrix, the element at the middle of the row of a 3 by 3 matrix was multiplied by minus. Then you establish the intersection of the row and column at that element. After that, you multiply the matrix, like you get the determinant of the matrix underneath it. Key properties about a matrix from the point of view of invertibility. Okay, so determinant of A. If it's different than 0, then A is an invertible matrix. It means that we can obtain the inverse of A. If the determinant is equal to 0, then A is called a singular matrix. It has no inverse. Second, multiplicative property. Determinant of A times B is equal to determinant of A dot product determinant of B. Okay. Transpose. Now, yeah, that A dot that B, it means you multiply the elements of A and B one to one, unlike the normal matrix multiplication that we've seen previously. Okay, so determinant of A matrix multiplied by B matrix, which is done by multiplying at first A times B. Okay, we multiply each row by its convenient column to get each element, just as we've seen before. After that, the matrix that we obtain, we get the determinant for it. Okay, so this is equal to determinant of A, which will give us a number actually. Okay, determinant of matrix A multiplied by determinant of matrix B. So determinant of A times B, when we multiply two matrices and we get the determinant, it would be equivalent to the determinant of the first matrix multiplied by determinant of second matrix. Okay, determinant of first matrix will give us a number value. I'm sorry when I said, we multiply element by element. Actually, determinant of each matrix would give you a number. You multiply one number, one value, you multiply them together, you would get a value equivalent of determinant of the multiplication of A with B. Okay. Transpose, the determinant of the transpose of a matrix is equal to the determinant of the matrix. Okay, so that of the transpose of A is equal to that of A. Okay, doesn't make much difference. Row column operations, swapping two rows changes sign of determinant. Okay, so multiplying a row by K multiplies determinant by K. Okay, adding a multiple of one row to another, determinant would be unchanged if we add a multiple of one row to another row. Multiplying a row by K, it multiplies the entire determinant by K. Swapping two rows changes sign of the determinant. Determinant of a 2 by 2 matrix. So for A equal ABCD, the determinant would be that of A is equal to AD minus BC. As simple as that. That would be the most simplistic form of a determinant value. As an example, you have A is equal to 3, 5, 2, 7. Okay, so determinant of this matrix is 3 times 7 minus 2 times 5, which is 21 minus 10, is equal to 11. For a 3 by 3 matrix, let's say A is equal to A11, A12, A13, A21, A22, A23, etc. Now here, if you notice something, each element is designated by these indexes. What do they mean? So A22, for example, it means that this is the value at the second row and the second column. This is the second row here. That's row 2. And this is the second column, column 2. Now, A33 is at the third row and third column. The first number, the first index, refers to the row, and the second one refers to the column. So, for example, A131 designates the first row and 3 the third column. And correctly, this is the third column here, and this is the first row. So we expand along with Laplace expansion. Determinant of A is equal to A11 multiplied by, you scrub the row and the column where they intersect at this number, A11 times the determinant of A22, A23, A32, A33 minus A12, here we have a minus. Also, you bar the intersection of the row and the column at this number, which has a minus sign. So minus A12 times the determinant of A21, A23, A31, A33. Plus, finally, A13 happens to be positive, okay, because it is an odd index. A13 multiplied by the determinant, which is, in such case, you have A21, A22, A31, A32. So let us continue with that. As an example, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's get the determinant. So 1 multiplied by 5, 9, 6, 8, which is 5 times 9 minus 8 times 6, which is 45 minus 48. Then minus 2, you see here, multiplied by determinant of 4, 6, 7, 9, which is minus 2 times 4 times 9, 36, minus 6 times 7, 42, plus 3, here it is plus, multiplied by 4 times 8 minus 5 times 7, or the determinant of 4, 5, 7, 8. So plus 3 times 4 times 8, which is 32, minus 5 times 7, which is 35. This becomes 0. So as a result, we deduce that this matrix is not invertible. Why? Because the determinant is equal to 0. Simplification of a matrix. So let's say we have a matrix. We have another way to evaluate the determinant, another method. So you have 2, 4, 6, 1, 3, 2, 3, 8, 5. The first step is we swap the second row and the first row. So you get, okay, you remove 1, 3, 2 to the above and 2, 4, 6. So we've swapped the second and first row. So the second row have become the first row and vice versa. After that, R2 is equal to R2 minus 2R1, meaning we are doing a combination here. We are doing a linear evaluation. So the second row is equal to the second row minus 2 times the first row. So it's like eliminating factors in an equation, basically. So R2, the new value for R2 for the second row is equal to R2 minus 2 times R1. This gives us, okay, so R2 minus 2 times R1 is equal to, you have 2 below minus 2 times 1, which is 2. That's for the first element. Then 4 minus 2 times 3, which is 6. Then 6 minus 2 times 2 minus 4. So you get 2 minus 2, 0. Then 4 minus 6 minus 2. Then 6 minus 4, which is 2. You see? This is the new row, which is the point. At the same time, we have R3, the third line, is equal to R3 minus 3R1. So we are trying to triangulate the matrix so that the determinant evaluation would become much easier. Now, for the third row, so R3 is equal to R3 minus 3R1, which means 385 in the third row minus 3 times R1. 3 times R1, which is, okay, minus 3, and 3 times 3 minus 9, and minus 3 times 2, which is minus 6. So 3 minus 3 is 0, 8 minus 9 minus 1, 5 minus 6 minus 1. You get 0 minus 1 minus 1, which is the third row. Now I need to work out the third row okay, the new third row, which is this one, in respect of the second row to eliminate, or the first row, in order to eliminate this part here. This line is equal to R3 minus 1 half R2. Why? So that the minus 2 would become plus 1. R3, which is 0 minus 1, minus 1, minus 1 half R2. So minus 1 half times 0, it's 0. Minus 1 half times minus 2. So it is plus 2 over 2, which is plus 1. Then minus 1. Okay, you get it? So this line, the third line, minus 1 half times the second line. So we add them together, you get, and you add them element by element, which is 0, 0, and minus 2. And you place that line on the third row. So we end up with 1, 3, 2, 0, minus 2, 2, 0, 0, minus 2. Hence, the determinant calculation becomes much easier, which is minus 1 multiplied by minus 2 times minus 2, which is 4, and minus 0 times 2, which is 0 anyway. So it is 4 times minus 1, which is minus 4. So the determinant of A is the product of diagonal entries times the sign you get from the swaps times the scaling factor. Compute the determinant of C. Okay, so delta or determinant of C is equal to 1 times, okay, this is, the easiest method here, I believe. So this is 1 times 1 minus, and here you have minus times minus 1 times 3, okay, which gives us, we will see the result at the end. So it is 1 multiplied by 1 times 1, then minus 1, which gives us plus 1 multiplied by 3, okay. Then you have 0 minus 0, but 0 multiplied by anything would give you 0. And finally, you have 2 multiplied by 0 times minus 1, which is 0, minus 2 times 1, okay? So the overall answer is 0, which means that this matrix is not invertible. Cramer's rule. Cramer's rule is a method to solve a system of n linear equations with n unknowns using determinants. Now, an important condition is that the number of equations should be equal to the number of unknowns. When the coefficient matrix, that's the second condition, the coefficient matrix should be invertible. In other words, the determinant of matrix A should be different than 0. Okay, so let A be a matrix of n by n elements, okay, n rows and columns. X is the set of variables or unknown, okay. B, actually it is the transpose here that we're dealing with. We're going to see how. And B is the set of, or the vector of constants, okay, set in a column, or constants column vector. The solution is xi, okay, for any variable is equal to determinant of A divided by, or determinant of AI. We will see how to get that. Okay, so we basically replace B, the vector of solution, that column, within the first column for X to solve X, then within the second column to solve Y, within the third to solve Z, and we divide that by the determinant of A. You get X and Y and Z. We're going to see it in a clearer example, where A of I is equal to the matrix obtained from A by replacing its ith column, okay, whether the first, the second, or third column, the first for X, the second for Y, the third for Z. So we replace the ith column by B, which is the vector column for the column vector for the solution. Okay, so B is the vector column for the solution, would replace either the first column in A, or the second, or the third, which would give us AI, okay, A of I, where I is equal to 1 or 2 or 3. So you get the determinant of that, and you divide it by the determinant of A. And this is how you get x, y, and z. As an example, solve 2x plus y minus z equals 3. That's the first equation. X minus y plus 2z equal 1. 3x plus 2z plus z equal 4. Okay, so what is A? A is actually these numerical values at x, y, and z. So x would be the first column, y the second, and z the third. So you have 2, 1, 3, correct? 2, 1, 3. Then what is being multiplied by y in the three equations is respectively plus 1, minus 1, and 2. So we have plus 1, minus 1, and 2. Then what is multiplied by z is minus 1, minus 1z, then 2z, then plus 1. So minus 1, 2, 1. This is A. B is the column vector of the solution, which is 3, 1, 4, correct? Now, at first, we need to evaluate the determinant of A, which is that of A is equal to 2, 1 minus 1, 1 minus 1, 2, 3, 2, 1. So it is equal to 2 multiplied by. Okay, let us help with this. So it is 2 multiplied by minus 1 minus 4, correct? Minus 1 minus 2 by 2, which is minus 4. Then minus 1 multiplied by 1 times 1 minus 3 times 2, okay? Which is 1 minus 6. Then for the third element, okay, you have minus 1. It remains minus 1, okay? The sign is plus. So minus 1 multiplied by 2, then minus 3 minus 1, so 2 plus 3, okay? We add all of that together, so the determinant of A is minus 10. So delta or determinant of A is equal to minus 10. Okay, x would be equal to delta x over delta, y equal delta y over delta, z equal delta z over delta. What do we mean by that? Okay, how to get delta x? Delta x, we get delta x simply by replacing the first column of A, which is 2, 1, 3, by the solution vector, which is 3, 1, 4. So you replace 2, 1, 3 here, the first column, by 3, 1, 4, and then you evaluate the determinant, which is called delta x. It is equal to 3 multiplied by minus 1 times 1, minus 2 times 2, which is minus 1 minus 4, then minus 1, correct, multiplied by 1 minus 8. Finally, you have plus, okay, the sign is plus, and the element itself is minus 1. So minus 1 multiplied by 2 minus 4 minus 1, which is 2 plus 4. Okay, 2 plus 4 minus 1. So all of that becomes minus 14. Okay, so x is equal delta x over delta, which is minus 14, divided by minus 10, correct? Or 1.4. That would be x, the solution for the first parameter, the first unknown. Okay, let us continue. Delta y, for delta y, you replace the second column, which was 1 minus 1, 2, by the solution vector, or 3, 1, 4, and you re-evaluate again the determinant for delta y. Okay, you get 0. So 0 divided by minus 10, which is delta, because y is equal delta y divided by delta, or 0 divided by minus 10 equal 0. Finally, for delta z, you have to replace the third row, which is minus 1, 2, 1, by 3, 1, 4. Okay, so you get 2, 1, 3, 1 minus 1, 2. The first two columns remain the same, but the third one has become the solution vector. Okay, 3, 1, 4. You reevaluate the determinant delta z, and what you get is 2 multiplied by minus 1 times 4 minus 2. Okay, minus 4 minus 2 times 2. Then minus 1 multiplied by let us clear everything here. So minus 1 multiplied by 4 minus 3. Then finally, 3 multiplied by 2 minus 3 minus 1, which is 2 plus 3 or 5. Multiplied by 3, which is 15, correct? So the overall value of delta z is 2. So we've gotten minus 14 for delta x, 0 for delta y, and 2 for delta z. Now let's get the solution for, or the value in other words, for different unknowns. So x is equal to delta x divided by delta, which is minus 14 divided by minus 10, or 1.4. Y equal delta y divided by delta. Remember, the determinant delta is delta of A without replacing any of the columns with B. So it is equal to minus 10 here. So y equal delta y over delta, or 0 divided by minus 10, which is 0. And z equal delta z divided by delta, which is 2 divided by minus 10, or minus 0.2. And that would be the final solution for the linear equations.